So this is the key to your Newton's Laws Test Study Guide. So I'm just going to go through each one quickly and hopefully you guys will use this to study. So for number one, defining the term force. In the previous unit we defined it as a push or pull. I also had people say that it is mass times acceleration, which is also true, and we learned that this unit, so that's a great job if you put that down. Number two, what is the unit of force? Anytime we exert a force on something, we've been talking about how we're going to label it with an N for newtons. Number three, defining inertia. You could find this in your Newton's First Law reading page, or simply just think of an example. We played broomball for this reason. When you're thinking about inertia, you need to think about the bowling ball versus the basketball. The bowling ball has more mass, meaning that it's going to have more inertia. And if something has more inertia, that means just like the bowling ball, it's harder to get it started, it's harder to stop it, it's harder to change its direction. So in other words, something with a huge amount of inertia, it's very difficult to change its current motion. So a good definition of it from your reading page would be the tendency of an object to resist a change in its motion. Something with greater inertia resists change more, just like the bowling ball. Number four, stating Newton's first law of motion. We've done this many, many times. An object at rest stays at rest, and an object in motion stays in motion unless acted upon by an unbalanced force. So number five, why is Newton's first law sometimes called the law of inertia? So hopefully you guys put some thought into this. What does inertia have to do with what we've just written on number four? And if you really think about it, inertia explains why things want to remain at rest or continue their motion. Okay, so number six, what is an unbalanced force? So first of all, you can think of it in picture form. This right here is an unbalanced force. You've got these up and down are balanced. You've got one going to the left while you've got a much larger one going to the right, so it's unbalanced. And so, in other words, an unbalanced force is where they're not going to cancel each other out. It's going to cause a change in motion or an acceleration, which we've talked about a lot. For number seven, what is a force diagram? This right here is a force diagram where you have a dot in the middle and you represent each different type of force with an arrow. And in a force diagram, you want to make sure that you're labeling your forces. Number eight, draw a force diagram for a hockey player sliding at constant speed across the ice. First of all, look for helpful wording within the question to help you along. Your wording here is constant speed. Anytime you have constant speed, that should automatically tell you that the forces in your force diagram are going to be balanced. So here is an example of what that force diagram could look like. Of course, depending upon the direction you thought the hockey player was going, these may be flip-flopped, but that's fine. Number nine, draw a force diagram for a bowling ball after it has left the bowler's hand. So that means that there is going to be no applied force. He cannot apply a force to the bowling ball once his hand is not touching it because it is a contact force. So the only forces acting on the bowling ball at that time are going to be gravity, normal, and friction. And this is going to be unbalanced because you have a force going to the right but nothing going to the left. And that means that the object is going to be slowing down, or in other words, accelerating, which is what unbalanced forces cause. Number 10, a little review. The difference between weight and mass. Mass is the amount of stuff in an object, which means it never changes, while weight is the amount of gravitational force on that mass. So it changes when gravity changes. So, putting this into use, how would an object's mass change if it were sent to Jupiter? And how would its weight change? Well, how would an object's mass change? Those two words do not go together because mass does not change. So anytime you see that, that should be kind of a trigger in your brain to think, nope, that's not going to happen. But its weight, though, if we take it to Jupiter, Jupiter's a little bigger than the Earth. So while its mass is never going to change, the weight would become much greater. Earth has a gravitational force of 9.8, while Jupiter's is much higher. Number 12 comes from one of our worksheets, so hopefully you got this. The sheet of paper is able to be pulled from underneath a milk carton because the milk carton has inertia. It does not want to change its previous motion. It was at rest before and it wants to stay that way. Number 13, compared to a 1 kilogram block of solid iron, a 2 kilogram block of solid iron has twice as much inertia because it has more mass. It has twice as much mass because it told us so. It has twice as much volume because it's going to take up twice as much space, so your answer has to be all of the above. Stating Newton's second law of motion. All you really had to do is say F equals ma, or force equals mass times acceleration. And this is a really good spot to put your handy triangle in there, especially with units, because you want to get used to using them. Number 15, how does the direction of an object's acceleration compare to the direction of the net force? And explain. Okay. So first of all, I drew myself a little force diagram of something that was accelerating because the forces are unbalanced. So the net force on here is going to be in this direction, and so your object is going to accelerate in this direction, so your acceleration is in the same direction as the net force. So drawing pictures is a really good idea if you want to work something out like that. If an object is moving at constant velocity, what does that mean about the forces on that object? Well, we kind of saw this on the first page. When you see constant right there, that means it's not accelerating. And if something's not accelerating, the forces have to be balanced. Okay, number 17. Can an object ever be accelerating when the net force on the object is 0? And explain. So I just picture this force diagram up here again, but then I make this arrow, I pretend that it's the same length as the other one. If I pretend that, that means that every single force is going to be balanced. Okay. Net force is 0. There's no force that's greater than the others. And so that means that the object cannot be moving. It cannot be speeding. Well, I take that back. It can be moving. It cannot be speeding up. It cannot be slowing down, and it can't be changing direction. So in other words, no, it cannot be accelerating. 18. What net force is required to accelerate a car at 2 meters per second if the car has a mass of 3,000 kilograms? So we're given, so this is what we're looking for. It says what net force, that's the first step. And then here's our acceleration. It says to accelerate a car, and then it gives us the mass. So we have mass, we have acceleration, we're looking for force. So I just subbed them in, m times a, there you go. Make sure you don't forget your units, and for goodness sakes, write your work. That is where most of the points you're missing is coming from, and that's just silly, because all you have to do is write this. So, write your work. Okay, we talked about this in class. What is the mass of a falling rock if it produces a force of 147 newtons? We talked about the acceleration of falling objects, and we looked at the bowling ball and the feathers falling at the same speed. Everything falls with an acceleration of 9.8. So we knew force. So I subbed that in. We knew acceleration. And then I used my triangle up there, and it says mass equals force over acceleration. So 147 over 9.8 gives me 15. Number 20, your own car has a mass of 2,000 kilograms. If your car produces a force of 5,000 newtons, how fast will it accelerate? So we have mass, we have force, so this time we're looking for acceleration, which means that we're going to take force divided by mass, and that'll give us our 2.5 meters per second squared. Okay, coming to the end. State Newton's third law of motion. This is the action and reaction law. So for every action force, there is an equal in magnitude and opposite in direction reaction force. Number 22. Explain the phrase equal and opposite. It explains the forces in an action-reaction pair. They're going to have equal strength, but opposite direction. Number 23, imagine you throw a ball. Upon release, the ball flies off across a field. What are the action-reaction forces, and why does the ball move faster than your hand? So, first I identified my action-reaction. My hand pushed the ball forward. The reaction is for the ball to push my hand. Just kind of reverse the two. And why does the ball move faster than my hand? The ball has less mass. Remember, force equals ma. And so it's telling me the ball has greater acceleration. Well, for something to have greater acceleration with the same force, that means that the mass has to be less. Okay, it's the butterfly in the windshield question. Hopefully everybody knows this answer by now, okay? If I ask you who feels more force, the butterfly or the windshield, I hope you all are able to get this by now. Ta-da! We've talked about it several times, so hopefully you know that. Number 25, a player hits a ball with a bat. The action force is the impact force of the bat against the ball. The reaction to this force has to switch them up. If the impact force is the bat against the ball, then you just reverse them. The ball against the bat. There you go. So essentially you kind of read it backwards. 26. Mass is the amount of matter or stuff contained in an object. Mass does not change with changes in gravity. And the acceleration of any object falling to the surface of the earth is 9.8. We talked about that in our notes, so hopefully that was easy for you. 28. Describe what happens when identical objects are dropped on planets with different gravity. You saw this in your virtual lab where you were dropping objects next to each other and you were deciding what location you wanted to drop them from. So an item dropped on a planet with the most gravity is going to fall the fastest, because on Jupiter, if we have a gravity of 25.4, that's going to fall much faster than 9.8 meters per second. It's going to fall 25 meters per second. So, describe what happens when different objects are dropped under the same gravity. We saw this when we looked at the vacuum. Remember that in real life, air resistance prevents this, but if there were no air resistance, under the same gravity, all objects would fall at the same rate. We watched that video with the bowling ball and the feathers. Number 30, an 8 kilogram object has a weight of 24 newtons on another planet. What is the G on this planet? You can use F equals ma for this. You have mass, you have a force, and you're looking for the acceleration, or G, on that planet, because they end up being the same, if you look. So, solve for acceleration, force divided by mass, it would fall 3 meters per second. So what is the weight of a 24.52 kilogram TV dropped on Pluto? Pluto has an acceleration of 0.59 meters per second squared. Well, we know the mass of the TV and we know the acceleration. And remember that weight is simply a force in newtons. So essentially we're just solving for F. So 24.52 is our mass, 0.59 is our acceleration, multiply the two, and you get your answer, which is in newtons. And weight is in newton because it's a measure of the amount of gravity on your body. Last but not least, good luck everybody.